class we have discussed about the resonance and the orthoparadirecting nature, orthoparadirecting groups, how they are associated with our chemistry and the organic chemistry reactions that we have already discussed in our last class. So today in this session I will be discussing only 2 to 3 parameters regarding resonance, and after that I will be moving towards the hyperconjugation and the other stuffs. So initially, as we have all discussed, that we have seen resonance is of course a parameter which is actually only existing in plane of paper, which has no experimental evidence. Now you can ask me that if the resonance have no such experimental results or experimental data, then how can we discuss or how can we see that resonance so much of important? For example, we can take this sort of thing that we have discussed about this resonance, this principle. Now you see that here are 3 carbon-carbon double bonds and 3 carbon-carbon single bonds. Now, from the experiment, what we can understand that all of the 3 bonds, they have such a bond length. Which is in between this carbon-carbon double bond and carbon-carbon single bond. That means all of these bonds have a partial double bond nature or a partial single bond nature, which actually depicts this phenomenon that sometimes this bond makes double bond, alternate time the resonance is taking place, and we are having like this sort of structure like this, where we can see the alternate bonds have gone a single bond nature. So from here we can understand that this carbon-carbon bonds are not a pure carbon-carbon double bond or a carbon-carbon single bond, which means there is a partial double bond nature of these 2 carbons. So this is actually the parameter which is actually stated by resonance. Now, as I have mentioned, you can see the resonance is only depicted in the plane of papers, and the canonical structures, that is the resonating structures we call them canonical structures. So these canonical structures, they don't have any physical existence. We only take them to explain our reactions, and we take the most stabilized form to explain any sort of reaction. So regarding that, we have discussed already in our last class that how these resonating structures, they direct towards a chemical reaction, they direct how a chemical reaction is being formed, or like what will be the products. Now in this class, the next point, which is most important, that will come into this thing, that regarding the hydrogen bond resonance. This is known as the hydrogen bond resonance, which we call collectively as a hyperconjugation. You can understand from this term of hyperconjugation, that means an extensive conjugation. Hyper means an extensive parameter, and hyperconjugation means an extensive conjugation. Now, how is this case happening? Let's say we have a molecule like this, CH2, double bond carbon CH, single bond CH2, and here is one hydrogen. Now I will explain you that this hydrogen is acidic in nature. Now you'll ask me that how is this possible? How is this so much of acidic in nature, and how we can explain? Now there are 2 parameters through which we can explain these things. For example, experimentally, if you want to explain, then I can give an example. For example, there is an acetylene molecule. Acetylene. Now, if you treat this acetylene with the sodium hydroxide, which is a base, that's OH minus, this OH minus will capture this hydrogen proton, and these two electrons will come over this carbon, and this will form a like this carbon ion, which means this hydrogen is acidic in nature. Now, why this hydrogen is acidic in nature? This is an experimental finding. That's how we can explain that this is acidic in nature. And regarding if we want to explain it with a theoretical formula, then we have to consider a common thing which is very much common regarding the parameters which we call as S character. S character. This is actually a percentage. That is the percentage of S orbitals present in any atom or any hybrid molecule. For example, let's say we have a carbon-carbon single bond. We have carbon-carbon double bond, and we have carbon-carbon triple bond. Now, each and every step, you know that carbon-carbon single bond is sp3 hybrid, carbon-carbon double bond is sp2 hybrid, and carbon-carbon triple bond is sp hybrid. Now, if I tell you that what will be the S character of each of this every system, you can easily tell that here is one S orbital out of 4 hybrid orbital, 3p and 1s. So that will be, of course, like 25%. This one will be 33%, and this one will be 50%. Now you can understand from this point that the percentage of S orbital in a hybrid orbital. That means, for example, if it is an sp system, here is one S and here is one p. So that means there are 2 hybrid orbitals, out of which one is S and another is p. So there are 2 hybrid orbitals, one S orbital. So 1 by 2 into 100, that will be 50%. So this is the S character parameter. Now we know that the S character, as the S character will be higher enough, the more will be the tendency of an orbital to extract the electron density towards itself, which means the basicity will be high. Which means the basicity will be high. So automatically this satisfies that we have discussed about the alkene system. So alkenes are more, that hydrogen, the alkene hydrogen, it is more basic than the alkyne hydrogen is more acidic than alkene. So like that way we can understand that okay, this one is acidic in nature. So let's say how it is happening in this case. So this hydrogen, this one will form a double bond over here. This one will get minus. So we'll see a resonance. This is the resonating symbol. We'll understand that it will be CH2 single bond CH, double bond to CH2. Here it will be minus with the 2 electrons, and here will be the H plus present. Now one thing to note, that this hyperconjugation means that H plus is not getting out of the system, it is present inside the system. It's just only depicting that how this resonance is getting happened. So likewise, this will have a stability factor, like that sort of resonance. Now, very common example, how we can explain this thing. This is a very common problem which all of you have encountered, I guess. It's very common for all of you, and all of you have encountered this problem. CH3 carbocation, CH3 CH2 carbocation, CH3 CH CH3 carbocation, CH3 C CH3, CH3 carbon. Now we are going to discuss about the relative stability of all the three molecules. You see that in all three cases, there is one thing is common, that here is one alpha carbon, here is two alpha carbon, and here is three alpha carbon. And we know that in case of any resonance, if we have a carbocation like this, and we have a carbon center like this, which is an alpha, so all of the three hydrogens can take part into resonance. All of the three carbons, they take part into resonance, and you will get, that is a hyperconjugation resonance. Of course, it's not like the very simple or the normal resonance. It's of course a hyperconjugated resonance, and you can see that there are three hyperconjugative structures. So we can say from here that as the hyperconjugative structures are more, the stability is more. So one thing, if we have an alpha carbon which have an alpha hydrogen system, and if it has a very some number of alpha hydrogens, they will have a lot of stability. So keeping in this mind, we will discuss the same thing, that here we have no alpha hydrogen, no alpha carbon. Here is one alpha carbon, here is two alpha carbon, here is three alpha carbon. So the alpha carbon hydrogen, here is nothing, here is 3, here is 6, and here is 9. So automatically the hyperconjugative structure, here is nothing, here is 3, here is 6, and here is 9. As we know the number of replaceable hydrogen in the hyperconjugative structures, so that will be the mode of the hyperconjugative structures, and mode will be the stability. So of course we can understand that this 3 degree carbocation will be more stable than the 2 degree and the 1 degree and the 0 degree. So from here we know that a 3 degree carbocation is more stable than 2 degree than 1 degree. This is for carbocation. This one we need to keep in mind in very strict and very formatting way. Another example, this one we will be discussing when we will be discussing about the reaction mechanisms. There we will be finding that how this is actually enacting and how this is actually perturbing the system of a reaction. Next example, which is commonly we know, very simple. Let's say here is benzene with 1 methyl, that is toluene. Next we have isopropyl benzene. Next we have tertiary butyl benzene. Like this. So now, and of course there is another one is ethyl benzene, CH2CC. Here you see the system is here. This alkene is the system. With respect to this alkene, this one is alpha carbon. So here we have this one is alpha, this one is alpha, this one is alpha, and this one is alpha. So alpha carbon 1, 1, 1, 1. Alpha carbon hydrogen, here is 3, here is 1, here is 0, and here is 2. These two hydrogens. This one hydrogen and these 3 hydrogens. So hyperconjugative structures 3, 1, 0, 2. Which means that this one will be a more nucleophilic. I am just explaining this one, that how it is getting a nucleophilic character. This one will be more nucleophilic. This one will be also more nucleophilic, and this one will be also more nucleophilic, but this one won't be nucleophilic. How this is happening, I'm just telling you. For example, let's say this one is compound 1, this one is compound 2, compound 3, compound 4. So let's say if we have these 4 compounds, then we can understand, just erasing the last parts like this. Here you can see, I'm just explaining this, how it is getting this sort of hyperconjugated structures. CH2 hydrogen, like this. Okay. Now this hydrogen that will come into the resonance, this one will be taking place. So we'll find the hyperconjugated structure. This is the hyperconjugation. So we'll find the hyperconjugated structure like this, minus double bond CH2 and here it will be CH plus, like this. As usual, this one will be minus, this one will be again minus. Again, this one will bond here and this one will be minus. So automatically this one will be orthopara directing towards electrophile E plus, and of course as usual meta directing towards a nucleophile. The same case as we have already discussed. Now this orthopara directing nature, this one will be of course different for this 1, 2, 3 and 4. How it will be, as we have seen that number of hyperconjugated structure, as it is the more will be the stability, so more will be the orthopara directing nature. From here what we can understand that 1 will have the highest orthopara directing nature. After that it will be number 4, after that it will be number 2, and last it will be number 3. Regarding orthopara directing nature towards electron. I think this is much clear to everyone, and this is the great what we call about Baker-Nathan effect. Very, very important topic for everyone. This is what we call about the Baker-Nathan effect. I think this is clear to everyone. So hyperconjugation, we have seen that okay, so if there is an alpha hydrogen towards an alkene or a reactive center, there is a possibility of a hydrogen bond resonance, what we call about the hyperconjugation. Last, the 2, we have the mesomerism over here. Mesomerism is basically the conjugation. Mesomerism is basically the conjugation. The mode will be the pi electron conjugation. The mode will be the conjugation. The mode will be the stability. The mode will be the stability. So this as simple as that. I guess this will be the same as we already discussed regarding the resonance. But the last part, which will be most important, that is the inductive effect. I think this one is very, very important for everyone. Inductive effect, what we call about the electromeric effect. Electromeric effect. This one will be very, very important for all of you. Sorry. So what is this? Scientists have described regarding this electromeric effect or inductive effect. Let's see how. For example, we have a carbon, carbon, carbon and Z. Z is any sort of group. Now they have chosen this carbon center to find out the electron density over this carbon center, and they have predicted that this Z has two categories. One category that will have an electron pushing effect, and then will have an electron pulling effect. That means, let's say I have some examples. Electron pushing will be the most alkyl groups like ethyl, methyl, isopropyl, etc. etc. All of these will be electron pushing. They will be pushing the electrons towards the Z or the carbon. Electron pulling means the outer negative or the electronegative, like OH, NH2, NO2, CHO, etc. etc. So, what is it is actually meaning? It is meaning like this way, that if we change the molecule for example CH3NO2 and CH3 we are considering this carbon center. Of course, due to this methyl group, electron will be pushing towards this carbon center. So here we can say this one has a plus I effect, or an electron pushing effect. And here, as nitrogen is more electronegative, so it is pulling the electron density from the carbon towards itself. So it has a minus I effect, what we call about the electron pulling effect. Only thing we have to keep in mind that if there are C, 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 and here is an X, that is an electron pushing or pulling group. If it's an electron pushing group, then it will be delta minus. So if this is an halogen, of course, so this one will drag the electron density from the carbon. Carbon will be delta plus. This carbon will automatically attract the electrons from the adjacent carbon. This one will be delta delta plus. This one will be carrying like this, so it will be delta 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 plus. The next carbon has no effect. So you have to keep in mind that only inductive effect has the effect till the three adjacent carbon atoms. After that, they don't have any sort of effect towards any compound. Let's say I'm giving you an example of electron pushing and an electron pulling effect. Let's say here is CH3, let's say CH2H, CHH, 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 and chlorine. If this is the case, then this chlorine, as this one is more electronegative, so this one will drag the electron density towards itself. This carbon will be delta plus, so this one will be highly acidic. This one will be delta delta plus, so this one will be mild acidic. This one will be delta 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 plus, means very small plus cation. This will be least acidic. This one has no effect, as this one is present very much far apart from the reactive center. I think this is clear enough. This thing we need to keep in mind that when we will be discussing about the structures, the resulting structures and the reactants. So we have seen resonance, inductive effect, hyperconjugation, mesomerism, all the four we have already discussed, we have seen completely. Now, there are two parameters of resonance which is very important. That will be the last topic that I will discuss regarding the basic principles. One is extended conjugation, another is cross conjugation. These are the two extensive part of resonance. Extensive conjugation means extensive conjugation. Let's say we have this OH over here and here is NO2. So I guess lot of you have already noticed that what will be the case and how it will be the case. What will be happening in this case? These two electrons will be coming here, this one will be double bond, this one will be coming here and this one will be coming here. Again the double bond will form over here, this one will be coming here, this one will be going here, and this one will be here. So you can see that this electron is getting transversed from here to this NO2 and then again coming back, which means this is actually an extended conjugation, else it would have been into this circumstances only. But here, as this is an plus R group and this is a minus R group, so one is donating the electrons and another is accepting the electrons. So this is like extended conjugation and the system will be very, very much stabilized in this case. And if we go about this cross conjugation, let's say it's a very common example, CH3 C double bonded O, CH hydrogen H, C double bonded O, O, ET, like this. Let's say here we are having a carbon atom like this. See what is happening over here. These two electrons, they get into resonance like this. This carbonyl will get single bonded like this. This can alter all, and another it gets delocalized like this way. This one can get minus, vice versa. This one can again get the same thing. This one can get minus. So you can see this minus, they can move somewhat of like this way. Also they can move somewhat like this way, which means it is getting cross conjugated. So overall the thing that this one is getting a cross conjugated in this particular phenomenon, isn't it? And of course this pays a lot of stability towards the carbon-carbon synthesis. So of course resonance is highly stable. More than that is the cross conjugation. More than that is the extensive conjugation. This is how the stability is actually looking into the system. I guess this is fine for everyone. So when we will be keeping or we will be solving the problems, we have to keep in mind that which are the following things which are more important to explain a reaction. And regarding that, we have a thumb rule that I want to discuss at this last point of our class, that of course resonance will be the first parameter which will be more focused. After that hyperconjugation, after that mesomerism, after that inductive effect. Now, so that means if a molecule is stabilized by resonance, even if the product is not satisfied with hyperconjugation or mesomerism or inductive effect, that doesn't matter. It of course it will form that sort of molecule or that sort of product where the resonance will be satisfied. So this one will keep in mind that resonance is much more fundamental than hyperconjugation, than mesomerism, than inductive effect. So This thing will to keep in mind to explain any sort of reaction or reaction intermediates, that how it is forming, how it is taken into the place, and how it is absolutely making the reactions feasible, such that we can explain each and every step. We can ascertain that whether the reaction is going in this way or that way, or vice versa, so on and so forth. So like that way, we have discussed the basic principles of resonance, and I think this is the last part where we have come, that we will discuss the last part, which is known as the steric inhibition of resonance, and how the steric parameter that we have discussed in the last class, that steric factor or steric inhibition of resonance, this one is very, very important. For example, we have an aniline molecule, or let's say here is NCH3, lone pair of electron, and we have like this molecule here NCH3, CH3. Here is also CH3, and here is also CH3. Here is also a lone pair. I think everything is visible to you. Now this one can easily take part into resonance. So here is resonance is possible. But here we can see that this resonance is not possible. Now the question is, why it is not possible? For that we have to think, and we have to see the exact structure of this molecule, what it is actually happening in this case. In this case, let's say I am just drawing the structure initially. Let's say this is the structure. Here is the filled lone pair of electrons, and here is the pi electrons. These twos are bonded, these twos are bonded, and these twos are bonded. And you can see both of them are parallel, right? So they can take part into resonance. But in reality, if we replace here the CH3 groups here, then this CH3 and these CH3 hydrogens, they will form a hydrogen-hydrogen repulsion, vice versa here as well. And this bond will get rotated. This bond will get rotated because of this hydrogen-hydrogen repulsion between this CH3 and this NCH3. Now what will happen in this particular case, you will see like this way, the benzene ring is just like the same that we have drawn. Now this bond will be an beta, and this one will be an alpha. These lone pairs, this one is like this, parallel to the plane. 1, 2, like this, and these electrons, they will get like this way. Now you can see, one is, previously they were like this, now they have tilted or twisted like this way. So now these two are not parallel into the plane. So likewise, this bonding is not possible right now. If there is one CH3 and here is one CH3. So now this overlap is not possible. So hence, we can see that this cannot take part into resonance, and this we will actually call about steric inhibition of resonance. So this was the last topic that we have actually concluded over here. This is all of the things that we have discussed about resonance, hyperconjugation, memorization and all. I think this one is clear to you. In the next class, we will be proceeding towards the solution of chemistryforfun and everything. That will be coming into our next video. Stay tuned for it, and of course, like and subscribe my channel. If you have any doubts, you can directly mail me. The email address will be given to you in our description box. You can go through that one, and stay tuned for the next video. Thank you very much.